we get started, it's my pleasure to introduce Laurent Bako. Laurent is an associate professor of control theory and signal processing at Ecole Centrale de Lyon in France. And he's spending his sabbatical here with us. So he's sitting in the robotics building. He will be around next semester as well, and he's actually teaching nonlinear control next semester. So if you haven't taken nonlinear control, you will probably take it from him. All of his degrees are from universities in France, and I won't try to pronounce them because I don't speak French. But he's an expert in system identification and optimization. He has served as an associate editor of many control conferences and recently appointed as an associate editor for tech. He will talk a little bit about his research on state estimation and system identification, a resilient way of doing that. And I am sure he will be happy to talk to you more. So if you want to talk to him, just shoot him an email and you can meet and talk.
Thank you. Thank you very much, Nick. Okay, thank you for the nice introduction and for hosting me kindly in your group. I've been here for 3 months. It's so far it's very good, and I like the weather and the environment. so far, it's very, very great. Okay, thank you all for coming to my presentation. I will be talking about state estimation and system identification. But first, I will probably talk about my institution, Ecole Centrale de Lyon. I guess that none of you has heard of it. So I would like to say a word about it. It is an engineering school in the suburb of Lyon, College of Engineering, founded in 1857. In terms of size, in terms of number of students, it is a small engineering school, maybe 5 times smaller than the College of Engineering of University of Michigan, for example, 1,600 students. But it is a quite prestigious, I would say, engineering school in the French standard, okay? It's ranked 7th nationwide, and we prefer to think that it is the first engineering school out of Paris, huh? Because we cannot compete with people from Paris. Okay. Lyon also is a very nice city. If ever you want to visit, this is an opportunity to come. We are organizing in next year a conference, an IFAC conference, MICNON. So if you want to visit, this can be an opportunity. Please submit papers. Okay. First, I will probably give an overview of my research topic, and then I will go to the main topic of today's talk. Okay, I've been working in the recent years around these 3 topics, essentially estimation, okay, which takes 2 facets, system identification, state estimation. I'm also doing a bit of analysis of systems, stability, and performance. So the common tool I'm using in all these topics is optimization. Okay, I'm using optimization in everything, almost everything here. Okay, so identification is what we call data-driven modeling. It's a kind of subtopic of also machine learning. People can call it also machine learning. Okay, so it's about modeling system. So a system can be viewed as a certain causal relationship between a set of signals. Okay, a model of that system is a mathematical description of the system that can be used in almost any engineering, system engineering. We need a model. We need a model for almost everything. We need a model for control, design. We need a model for simulation, prediction, analysis, filtering, fault detection, etc. So the question is how to obtain that model. Okay, there are 2 ways essentially of obtaining a model. First, we cannot construct a model by just applying the physical principles governing the behavior of your system if they are well known. Okay, But in general, sometimes they are not well known. And even though they are known, sometimes there are parameters involved in those laws that we don't know, okay? So another way of constructing a model is by experimental modeling through data, okay? So you do an experiment on the system and you collect data, and based on those data, you construct a mathematical model that is expected to describe the behavior of your system, okay? In practice, so what we need is data. The first thing we need is data. So how to obtain data? You have to select the input. This is the input signal. You excite the system with that input. You measure the response of the system to the input. And by processing those data, you're going to construct a model. Okay, so we need data. And we need also a model class. We need to choose a model class, okay, with a certain representation power, okay? And then feed the data to the model by using optimization. And once you have a model, the question is it good enough? Is it a good representation of your system or not? So in the last step of the identification procedure, you're gonna construct some generalization tests to check whether your model is sufficiently good or not, to validate or invalidate your model. Okay. So a second topic I've been interested in is a state estimation. I think everybody knows about the state estimation. I will not spend too much time on it. I will just introduce it quickly. State estimation is about recovering a vector-valued signal, denoted here by xk, based on a certain prior knowledge of the evolution of that vector-valued signal, okay? And some measurement y related to that state, okay? Through a certain equation, which is called the state measurement equation, okay? So we are given those models. We are given f, we are given j here, we are given y, and we want to recover the state, but we don't know this kind of signal. W and V here represent what I would call noises or modeling errors. Okay. So the problem is challenging essentially because we don't know these things. Right. Okay, so my today talk is centered about actually state estimation. I will talk about more specifically secure state estimation, robust state estimation. So what is the state useful for? I think everybody knows what it is about. State is useful for state feedback control, for monitoring the system, or for fault detection. And in general, in many processes of practical interest, the state is not fully measured. So we have to estimate it, okay, from the measurement and from the prior knowledge of the model of your system. Okay, the challenge we're facing is that the data may be really unreliable, due, for example, to measurement noise, intermittent sensor fault, for example, or adversarial attacks on your sensors, okay? This happens frequently in cyber physical systems, for example, when the data needs to be transmitted to the estimator through a certain communication network, so the data can be attacked. And this generates some error on the data. And the question we are asking here is how to estimate the state in a certain robust way, despite the presence of these unknown signals, okay? So the unreliability of the data we model here with additive signal W and V, okay, which are assumed to be sparse because we need them to be structured somehow. But otherwise, they are arbitrary. They are arbitrary but sparse. Okay. Okay, this is not a new problem at all because there are already many work out there dealing with different facets of this problem in different settings. Okay, basically, I will divide the existing works into two categories. We have a group of methods dealing with state estimation in a batch offline setting. Okay, this is the majority of the methods here, and they are in general based on optimization. And there's another smaller category of methods which are not primarily framed for secure state estimation, but somehow they can be applied to this problem as well. Okay, so here the 2 points of my talk. First, I will talk about our work on batch state estimation offline, and then I will try to explain how we can extend this work for an online adaptive state estimation. Okay, so let us start. Consider this discrete time LTI system, a linear time variant of this form. It's very simple system model. W here and V are the disturbances, the noises, the unknown signal that we don't have, and X is actually the state. A and C are the system matrices that we are supposed to know. Okay. So the question is very simple: how to infer the states, how to estimate the states. So the model can appear very simple. Okay, I could have considered a nonlinear model, of course. In principle, for the method I'm going to present, nonlinear models can be addressed. But the problem is that we will end up with an optimization problem that we don't know how to solve correctly, because the problem will become non-convex, and so we cannot guarantee the obtention of the optimum. Okay, so first, notice that if the uncertainties here didn't exist, the problem would be really trivial. We would just need to require that AC, the pair EC, is observable. Okay. On the other hand, if the disturbances are completely arbitrary, there's nothing we can do. Of course, if they are arbitrary, there is no information we can get from the model, nor from the measurements. Okay. So we need really to assume something about those uncertainties. Sometimes they can be assumed to be bounded by unknown somehow, or we can put some stochastic assumptions on them. Okay. So the design of the estimator will be based on those assumptions. Okay. This is otherwise there's nothing we can do. So what we are proposing here is an optimization-based estimation. Okay.
I have a question. Do you need to assume they are independent with the time?
The independence of what?
I mean, the WT and VT are independent.
For now, no. I didn't put any stochastic assumption on the uncertainties, but this is possible. This is something we can do. But for now, these are general uncertainties. They can be deterministic. They can be stochastic. I didn't attach any statistical significance to those disturbances for now. Okay. So here, so we propose an optimization-based approach. We are going to select the estimates as the minimizer of a certain ranking function, a certain cost function denoted here by VT. And VT, we're going to select it this way. Okay. So there are 3 terms in this cost. So the first cost, I will call it the cost related to the initial state. The second one is the cost related to the dynamics. And the other one is the measurement cost. Okay, so what we are trying to do basically is to make the state, the estimate. This is the candidate state we want to retrieve, and basically we want to make the estimate consistent with the prior knowledge that we have. Okay, so this doesn't seem to be a bad idea. Okay, it seems quite logical to formulate the ranking function in this form. But the main question is, how do we select those costs, those as functions, phi 0, phi t, psi t? We need to choose them somehow, in a smart way. Okay, how to choose them? So in order to see what is going on, let us evaluate our cost, our ranking function at the true state. If we evaluate the ranking function at the true state, this is what we get. Okay, we get a function which depends on the initial state and the other disturbances that we don't know. Okay, but what we want actually is that the true state minimize this ranking function. Okay, So we need to select those loss functions, I would call them loss function, so that the true state is a minimizer of our ranking function. Or more realistically, we would like to have this kind of property, okay? So for any minimizer of our ranking function, we would like the difference, the error between the estimate and the true state to be small somehow.
I'm sorry, what was big N again?
Sorry, it should be T. Good point. It should be T. Okay, this is the number of measurements, yes. So it should be T there. Okay. Good. So what we are suggesting is the following. So suppose that the noise here can take very large values. Then if you choose phi t to let them grow, then there's no chance that the true x will be the minimizer. So one way to choose those functions will be to select them in such a way that they prevent the noise to grow, okay? So in our case, we just assume sparse noises, okay? So Vt, for example, can take arbitrary large value. If Vt can be large, so whenever Vt is large, we want phi t to downweight it, okay? So that it is kept small. Otherwise, there's no chance that the true x be closer to the minimizer, okay? But following this reasoning, we can just say, why not just set everything to 0? But then if we set everything to 0, we get a function, a ranking function, which is not discriminative anymore, because it will not help us discriminate between the good states and the bad ones. So we need V to keep some injectivity property somehow, okay? Finally, we would like Vt to be convex, and you know why? Because we would like to be able to compute efficiently the estimate. Okay, this is the reason. And this is the reason why I select a linear system, okay? Otherwise, Vt, even though phi 0, phi t, and psi t are convex, if the model is nonlinear, then the global function will be non-convex probably, okay? Good. So some, how to say it, indication as to the way of selecting those loss functions. If the noises, the known signals are essentially bounded, in the sense that the majority of them are really bounded. For example, if there are, I would say, generated by a Gaussian distribution, for example, then selecting them as quadratic function is not a bad idea, okay? It can work, okay? A typical example is the case of the Kalman filter. Actually, the Kalman filter is a particular case of this framework for which all those loss functions are quadratic, okay? If you select all those functions quadratic in this form, you get the Kalman filter, okay? But what if those those uncertainties can be arbitrarily large if there is a certain non-negligible proportion of them which is very large, okay? Then we need to resort to robustness-inducing functions, loss functions, okay? Because we will see that the quadratic function in this case will not work anymore, okay? Good. Here's a graphical representation of a certain number of loss functions, okay? So one feature that is really important for a loss function to induce robustness is the growth rate, okay? Here, the blue curve represents the quadratic function in a scalar case, and we see that the quadratic function grows very quickly, okay? So if the noise happens to be large, as we have just seen, the quadratic function will amplify it more, so that we don't have any chance to get the good state, okay? Here, I just restrict myself to only convex function, but you have also other loss function which may present robustness properties. For example, the absolute value, there's that loss function called the Vapnik loss, the abs log loss, and the Huber loss, okay? Those increase, but they don't increase that fast. Good. So we want to design a state estimator, and we want to design it in such a way that it satisfies a certain property that we call resilience, okay? So what is it? A state estimator, like the one we have just seen, is called resilient with respect to a certain set of disturbance. E here, the disturbance has two components, W and V. W is for the process noise, and V is for the measurement noise. So the estimator is resilient to such a set of disturbance if the estimation error associated with that estimator is bounded by a certain continuous function of the distance between the actual disturbance, which I call here E, and the set big E. Okay, rho here is a K function, a function which is continuous, positive, definite, and increasing. Okay, so if the distance here is equal to 0, then we get the true state. So whenever the actual disturbance here lie in E, we get exactly the true state. Okay, but for this to be interesting, E should not be a trivial set. Okay, for example, the conventional robustness, the conventional concept of robustness applies to the case where E is equal to 0. Then the distance is just equal to the amplitude of the disturbance here. Okay, because the conventional idea of robustness is a continuity property. If the model deviates from the nominal representation, then the estimation deviates proportionally somehow. Okay.
Quick question. So in this definition, what is E? Is this for all E or
big E?
Small e?
Small e is the actual disturbance, the actual W, and the actual V, the actual process noise and the actual measurement noise. This is the E, a combination of the two.
Can you explain the consequence? I think even though E belongs, the small e belongs to the capital E, this can't imply the estimated state is the true state. I think.
Here is, if you consider the definition of the distance here, if E belongs to big E here, then the distance is equal to 0. And if the distance is equal to 0, we get 0 here because rho of 0 is equal to 0. And then here the error is exactly equal to 0. You get the true state. This is a property. Okay. So here is a result that I extracted from our paper here. It's just a special case of a more general result, which express resilience of a state estimator. Okay, if you take, okay, so define first the set of disturbance to which we want to be resilient. Okay, so we are not resilient at all with the process noise. We are only resilient with a certain set of measurement noise. Okay, a measurement noise which is sparse in such a way that V is a matrix from with all the measurement instances and noise instances, such that the number of columns in V which are non-zero is no larger than certain R. Huh? Okay, so in the previous estimator, if we just select all the loss to be the 2 norm, non-smooth 2 norm, we select the initial cost to be 0, provided that a certain observability condition is satisfied, we get the resilience property. Okay. So I will explain in a second what this one represents. Okay. This can be viewed as a certain observability conditions. Okay, so it is defined like that, but I will not comment it technically. I will just say that somehow this function here is a quantitative measurement of the observability, the degree of observability. The smaller it is, the more observable the system is somehow, okay? So if you want to interpret this bound, you will see that the more observable the system is, the more complex VR is allowed to be, okay? VR is the set of disturbance with respect to which we are resilient, okay? And the more observable the system is, the smaller the estimation error is going to be. Okay, good. Excuse me. So this problem could have been formulated as a regression problem as well. Okay, it's not very hard to write the system equation in this form. So this is a regression problem where the quantities in red here are unknown. Okay, so y bar t here is all the output stacked in a vector. OT is observability matrix, and that H is a matrix populated this way. Okay, then we could assume that if we assume that the process noise is equal to 0 and the measurement noise is sparse, we can formulate an estimator just of the initial state. I mean, the thing that we don't know in this case is just the initial state. Once we know the initial state, we just simulate the system, the model of the system to get the rest of the state. Okay, this is possible. This is something that is possible. Or if we assume that the process noise exists, but it is dense. It is dense in the sense that only a tiny fraction of its instances are allowed to be non-zero. Okay, allowed to be large. Sorry, but it is essentially dense. And VT is sparse. Then we can formulate the problem this way. Okay, so we can put a quadratic loss on the W here because it is dense. The quadratic loss is good for dense noises. And we can put an L1 norm on V because it is sparse. The L1 norm is known to tolerate sparse noises or to promote the obtention of sparse noises. Okay, so we can formulate this cost and constrain it by the system equation in this form. And then this is to obtain the initial state and an estimate of the noises. And once you have the initial state and the estimate of the process noise, you can simulate the system equation to obtain the rest of the state. This is also possible. And the ideas I've just presented can be extended to system identification as well. Okay. Suppose, for example, that you take a regression model of this form where y and phi are known. Okay, phi is the matrix of regression, y is the measurement, and v is the noise. Okay, in that case, we can prove that provided that a certain condition hold, which is very similar to the one we have just seen for observability, the estimation error will be bounded by a linear function of the distance between the actual disturbance and a set, which is the set of R sparse noises. Okay. This is for this kind of L1 or least absolute deviation estimator. Okay. So we get resilience in this case. And KP here can be interpreted as a gain of the estimator. Okay. So ideally, we would like the gain to be as small as possible. And for the gain to be small, this is a property of the regression matrix phi here. If you want the gain to be small, then phi should be rich somehow, very rich. Okay. So this quantity here should be large, and this one here should be as small as possible. Okay, good.
Is there a persistency of excitation type interpretation of that?
Yes, it's a quantitative yes, persistency of excitation concept, I would say. Okay, so this can give rise to experiment design, for example. If I want to find the phi such that these KPs as small as possible. So I need to select the input of my system in such a way that this quantity is as small as possible, for example, or this one is large somehow. Okay. Just a sample of simulation result. I will do two experiments. One where the noise component is actually in E, okay? And in that case, we can show that the error is equal to 0. Here, we presented the probability of exact recovery of the state versus the sparsity level of the noise, okay? We just put only measurement sparse noise in the model, okay? In that case, we see that for R, a non-trivial R, we get exactly the true state. Okay, so the second experiment is when we added everything. We have process noise, we have measurement noise, and the measurement noise is both dense and sparse, and the process noise is dense, only dense. Okay, and we compare a bunch of estimators. The notation here, what is the meaning? We have a epsilon which for estimator, and we have in the subindex you have two notations here. Here, for example, mean that the first cost, the state cost, is taken to be quadratic, and the measurement cost is taken to be L1. Okay, and what we see here is the representation of the relative estimation error versus the sparsity of the noise. Okay, we have everything. We have sparse noise, but we have also dense noise. But we present the result as a function of the most troublesome quantity, which is the sparse noise here, and the black line and the red one here are the baseline. I mean, the oracle estimation. This is the best we could get. We compare to the best we could get, and we see that the estimation error is reasonable until a certain point. If the sparsity levels grows too much, then the error start growing as well. So, any questions so far?
I'm trying to understand why do you have to penalize the discrepancy between in the state dynamics equation? The fact that you're penalizing the discrepancy in the output equation be sufficient to end up with accurate estimation?
I mean, it depends, okay? Because you can write the equation here as just one single, with one single perturbation here. We can just gather these two terms into one thing, okay? So, but then what is the assumption you put on it? Okay, it's easier to put an assumption on the process noise and to put an assumption on the measurement noise separately. If you combine them this way, you get a noise which is somehow complicated. But
it isn't. I mean, penalizing the state term very much depends on the basis that you express your state space in. So you're going to get very different results if you just change your coordinates, right?
Yes, but the state also will change.
Yeah,
I mean,
right. That's my point. So even the same estimator is going to perform very differently depending on the coordinate system that you use.
I don't know if you compare them in terms of relative error. I'm sure you're right, it's going to change. But I don't know in which extent, to which extent it's going to change, because the way you should compare them is to look at relative error, because the state will also change if you switch coordinates. And you should not compare them in terms of absolute error, but in terms of relative error. It's probably going to change. I didn't analyze this fact, but I don't know in which extent.
A related question. If you do a coordinate change, your W, instead of being additive, it will multiply the coordinate change vector matrix as well.
Yes.
Then your model on W needs to change as well.
Yes.
And with that change, this estimator should be still invariant. At least the bounds you are getting should be invariant. If you can model that like transform noise.
This is a good question. I didn't look into it. Yeah, it's a good question. So to be investigated. Yeah. Okay, good. Now let us try to extend those ideas into an online estimation setting, because in general, when you need the state, you need to get it online. When you need it for control, or when you need it for fault detection, for example, you need to estimate it online. Okay, so let us try to see whether we can extend the robust estimation algorithm that we have just seen to an online estimation setting. Okay, so one possible way to go along that, it would be to keep minimizing the cost function we have just seen for any t. For any t, we just keep minimizing it, and we take the last state. We estimate all the states from 0 to t, and we take the last one. This would be the exact way of extending the idea. But in that case, the problem we are facing is that the number of states is growing, the complexity of the algorithm is also growing, and this is impractical. We cannot do that, okay? So another way would be to use dynamic programming to reduce the complexity, okay? Dynamic programming, typically the way it works is that we try to do a first estimation, I would say formally or offline somehow through the equation, through the calculation. We do a first minimization with respect to all the state until t-1. We don't minimize with respect to the last state. So we get a function of only the current state. And online, we're just going to minimize that cost function, which is a function of only one state. Okay. This way we can reduce the complexity and keep getting exactly the result we could have obtained here. Unfortunately, the problem here is that you need to come up with a formal explicit expression of dv star here. And this is really hard if you take phi, the loss function, to be arbitrary. Okay, so this is not really good also. Another way would be to use a moving horizon approach. So we just limit the horizon of estimation to be finite, and then we move it, okay? So we can just fix it to be 10, we estimate 10 states, the 10 last states, and we take just the last one, like in the model predictive control, the same kind of principle, okay? And another alternative would be to just simplify the problem somehow. And this is what you're gonna do. We're gonna simplify the problem. And if we simplify the problem, the way we are going to say it, then we can take a nonlinear model here, okay, which can be arbitrarily complex, okay, the nonlinear dynamic here, okay. So we are going to consider now this kind of model, okay. FT is possibly time varying. I don't put the input here. The inputs are included in FT, okay. You can include input in FT. This is why it is time varying. But the measurement equation, we keep it linear, okay, for convexity reasons. Okay, so we want to get a robust optimization-based recursive state estimator. That, okay, we just formulated simply like that. Okay, the way we simplify the problem is that we renounce considering the process noise. We just ignore it somehow. And at each time t, what we do is that we predict the state at time t based on the estimation at time t-1 by applying the dynamics, okay? Then, for the measurement update, okay, we are gonna solve an optimization problem. And this final state is obtained this way, by solving this optimization problem. The idea is basically to select the final estimate to be close to the prior estimate. This is the one we call the prior estimate, while minimizing the measurement cost, a certain measurement cost that is defined this way, which is convex. I mean, it's the weighted cost, phi is convex, and this one is convex as well. Okay. So this we can solve it. And we can show that the state is given by a simple algorithm. This from a compact algorithm. This from using a proximal operator of this function. Here, everything is convex. You can compute it online efficiently. Okay. Just some brief reminder on what the proximal operator is. It is defined this way. For a function g from Rn to the extended real line, the proximal operator of G associated to any x, this kind of vector, the minimizer of this kind of cost function. It's a kind of projection of x onto the domain of G, but we are not just minimizing the Euclidean distance. We are minimizing the Euclidean distance plus a certain function, which is G here, okay? And first question we can ask is whether this thing is well defined. And it turns out that it is when G is proper, meaning that it has at least one finite value, it is closed and convex. Closed and convex, it suffices that it is lower semi-continuous to have this property, and this property is verified here in our case. So then in that case, the solution exists and it is unique, okay? And as we are going to see, the cost function that induce robustness are generally non-smooth. So the G function that we are going to minimize here are non-smooth. Okay, so in order to compute the solution, we need to compute the sub-differential of those kind of function. And the sub-differential is just a set collecting all the sub-gradients of our function. And the sub-gradient h of g at a certain point x is defined this way, okay? It defines all the tangent, so all the tangent to the graph of j at the point x here, okay? It turns out, again, that when g is convex, then the sub-differential is non-empty, okay? So the function is sub-differentiable and everything is okay. And if you want to compute the minimizer, then you need to use this condition. So x star will minimize g if and only if 0 is in the sub-differential set of g at x star, okay? This is simple to see from here. If h is equal to 0, then you get g of y larger than g of x for any y's. It means that x is a minimizer of g. Okay. So by applying this theory, okay, and isolating the error, the estimation error at time t, we are going to define it like that, is the difference between the estimate and the true state, okay? We can work out the dynamic of the error. The dynamic of the error here is the dynamical system, okay, with state E, okay? And indeed, it is an implicit system because we are not able, in a general case, to express ET as a function of ET minus 1, okay? So you can write it as an equation, it's an implicit system, and it is a nonlinear one, okay? Even though we assume that the initial system is linear, this thing is going to be nonlinear, okay? And psi t here is something which depends on the sub-differential of phi, okay? And then we get this result. First, we start wondering whether this thing will converge if there is no uncertainty. We want to check the observer property. Does it have an observer property? This we can prove it rigorously for a linear case. For a nonlinear case, I think it's also possible by requiring some Lipschitz conditions, but you have not done it so far because this is a work which is still ongoing. If we take a linear system and if it is uniformly observable, and if we assume that all the matrices here are uniformly bounded, and under some technical condition that I did not explicit here, we get that the error converge asymptotically to 0. This we can, and okay, for a phi which is positive definite, I didn't put it here. Yes, the phi should be positive definite. Good. And a remark is that, again, the Kalman filter is a special case of this framework, okay? For which phi is just selected to be quadratic. And the W here, I forgot to say what is exactly the W and the V are user defined. These are inputs to our algorithm. The user defined them, okay? And in the Kalman case, there are W is automatically recursively defined this way. So in the Kalman case, the input to the algorithm would be this matrix V and this Q. This V is going to be the covariance of the measurement noise, and this Q is going to be the covariance of the process noise in general. And in the Kalman case, you have a WT which is automatically defined this way. Okay, so it's a special case of our framework. Okay, good. And so far, what I presented for the online estimation is convex. It is solvable online. But to solve a convex optimization problem, it is an iterative process. And doing an iterative process can still be costly. Okay. So the question we are asking now is whether we can come up with closed form solution. Okay. And in order to get to this point, we need again to simplify the problem. Okay. And this is what we're going to do. Suppose that GT of Z, the measurement cost, we can define it this way along the sensors. Okay, there are NY sensors, and we can decompose GT as a sum of other functions, sub-functions here, and where in each one only the measurement of the sensor I intervenes. Okay, in that case, instead of doing the update for all the outputs at the same time, we do it for each individual output. Okay, we do it output by output. Okay, and then we get this algorithm. So at the entrance of the algorithm, we have the estimator time -1. Okay, and we iterate this kind of thing. And instead of using GT, we use GTI here. And at the end, what we obtain is the final update. Okay. Let us do it by choosing GTI to be the absolute value. Okay. If GTI is the absolute value of this form, so YTI is the ith measurement at time t. CTI is the ith row of the observation matrix CT. Okay, and lambda ti is a regularization parameter. Okay, and so what we need to do is just to compute the proximal operator of that function here, and it turns out that by doing some work, it's not that difficult to obtain, and we obtain it in this form. It's a function that contains a saturation, and you evaluate this course here. So it modifies X in the direction of A by a certain gain, which depends on this error. I would call it this error. It will appear later that it's the error, because basically it's going to be this thing. Okay, so our algorithm is going to be of this form then for the absolute value. So here we get a closed form solution, which is very, how to say, simple to apply, because it doesn't require optimization. We can just apply it. Okay, but this is a consequence of a simplification, of course. Okay, so now the question is, since we can do it for the absolute value, we can wonder whether we can do it for other loss function as well. Okay, suppose that we view the measurement noise as the contribution of two parts. One is bounded reasonable magnitude, the other one is sparse, potentially large values. Then the output can be written this way, and then we can apply something like the lasso that you probably know. Okay, we put here a square loss for this, which is supposed to be this bounded noise, and we put an L1 norm for this one, which is supposed to be sparse. Okay, and then we get something like that. And again, for this one, we can show that a closed form solution exists, and we can apply it. Okay, and we did it for a bunch of loss functions, the ones that I showed in the beginning. Okay, for the absolute value, we get something of this form. For the lasso type, we get this thing, etc. They have all of them the same characteristic. You update X in the direction of CT by evaluating the prior error. This is a prior error. You have X, you evaluate how X is good first. Okay, if this error is equal to 0, then there's not going to be any learning, because X is going to change. Okay, so this is how good X is already with respect to the measurement YT. And you have some saturation in them, okay? And the saturation naturally are robust, okay? So this is saturation that you get naturally from solving an optimization problem. It's not something that you just plug there artificially, okay? It comes from optimization. You have saturation almost everywhere, except maybe here, okay? And here you have both saturation and dead zones, okay, in this loss function. Okay, good. Let us look at an example on this. We take an example of this form, an LTI model. And look, this model is oscillatory, okay? If you look at the eigenvalue of A, this is a discrete time model. You look at the eigenvalue of A, they all are modulus 1, meaning that your system is not asymptotically stable, okay? So since the update of the observer using the measurement can be harmful, one valid idea would be the following. I just simulate the model in open loop. If A is asymptotically stable, I should converge to something which is good, okay? But here, A is not asymptotically stable. Then we really need the measurement, even though they may be harmful to the estimation, okay? And this is possible because AC, we can check here that it is observable. This is just to show in our experiment, I will do 2 experiments. The first experiment, I just use only sparse measurement noise. And the second experiment will just be with everything active, all the noises active. Okay? This is just to show how the sparse noise look like. Okay? This is sparsity measured in terms of the measurement noise when it is vectorized. You just look at it, you change the time scale, okay? You unwrap the time scale and you get something in this form. Okay, the noise can take very large values. And let us look at the open loop case. Suppose we just simulate the model we have. You get the curve in green here. You see that this is the error versus time. Here, you get the curve in green, it's not good. Of course, you agree that it's not good because the system is not asymptotically stable. You really need the input, okay? If you just apply the Kalman, the steady error Kalman filter, the steady state, sorry, Kalman filter, you get the curve in black, and you observe jumps whenever there is a noise instance that occurs, okay? And now we apply 2 of the algorithms that you have just shown. In blue, we have the lasso, in red, we have the L1, and you see that here they converge, okay? You have some solid line here that I call lasso Kalman, L1 Kalman. This proceeds from the following idea. Since the estimators are robust, somehow I can detect the bad data using those estimators. I do it in two steps. I use the robust estimator to detect the bad data and then remove them. And on the rest of the data, I apply standard Kalman, okay? See, you can do that, okay? And if you look closely at the curve, you see that there are some small variation of the estimation delivered by the lasso and the L1, for example, but for the lasso Kalman, L1 Kalman, they really get the good state, okay? Because they don't go, they don't oscillate, okay? Good. Here is a comparison of everything, okay? All the costs that I've shown with only sparse measurement, and versus the is something that I call the minimum dwell time. The minimum dwell time is the minimum time between 2 consecutive occurrences of the sparse noise, okay? And naturally, when the minimum dwell time increases, then the error decreases, okay? But all of them are robust somehow because you get an error which is small. Okay, so that's strong. Okay. Now in the second experiment, I just put everything. You have dense noise for the process noise. For the measurement, you have both dense noise and sparse noise, and you can see that we get an error which is somehow reasonable. Okay. Again, if we look at all the estimators again in the presence of all the noises, you still get estimators that are quite good. Okay, now for all the simulation I've done so far, the level of the saturation, I mean the weighting matrices, the parameters of the algorithm were constant somehow. Okay, I didn't do a fine tuning of them. One question we may ask now is, given those parameters, we are able to come up with an analytic estimator. Okay, now we can wonder whether we can somehow control them. So they can be time varying actually. They don't need to be constant. Okay, and something really interesting is okay. I didn't try to explain this one why it is so slow to converge. It is slow to converge because of the saturation. Okay, with fixed level, it would be good to have saturation with varying levels, so that to accelerate the convergence here. Okay. So the question we may ask is how to automatically somehow, through a certain optimization problem, select those parameters in such a way that the error behaves well. Okay, this is an open question. Okay, now to wrap up, what we have just seen is some optimization method for robust and resilient state estimators. So we have discussed first the idea offline. And in the second part of the talk, I've tried to extend those ideas to an online estimation set, okay? And we have more precisely come up with some closed form update formulas for a set of robustness-inducing or update loss functions. Okay, and the results here I presented them for state estimation, but they can be applied almost like that without change to adaptive system identification as well. Okay. Okay, the last part of the work is still under investigation, so we need to come up really with a formal assessment of the robustness property of the proximal observer that I've just shown. So we would be more particularly interested in a property like input to state resilience, okay? How to select the weight in an adaptive fashion. Okay. Good. Those are my co-authors, collaborators for this work, and this presentation is based on this paper. Thank you for your attention. I'm sorry for that.
And time for one quick question. Any questions there?
So thank you for the very nice presentation. So I saw you compared your proposed estimator against a standard, say Kalman filter. I would wonder, have you looked at any just real simple heuristic adjustments to the standard steady-state Kalman filter, where, for example, you do thresholding, and anytime your measurement is outside of that threshold, you disregard that measurement by essentially setting at that time step the Kalman gain equal to 0. And with those simple heuristic adjustments, do you get anywhere near the performance of your optimal estimator, or do you still do significantly better?
This idea, yeah, I thought of it, it could work if you allow a sufficient time between two consecutive occurrences of the sparse noise. If you have sufficient time, then the standard Kalman filter can converge, and then you can put your threshold to be able to detect the future occurrences. But if your sparse noise occur very frequently since the beginning, there's no way the Kalman filter will really converge so that you can use your threshold to detect the bad data.
Well, you could still, I mean, you could still, if I take a physical measurement, for example, by measuring an angular rate or an angle through an IMU, you still know from physical understanding of the device under control that certain values are not possible, right?
Mhm.
And if the measurement comes out as one of those values, then that measurement should be discarded and treated as if it's a mispackage.
Mhm.
And your ability to discard that data has nothing to do with whether or not the Kalman filter is converged, right?
Yeah, you can still do that. Yes. The question is the threshold, how you get it. This is
Sure.
the
I
big problem about it.
get that. I get that, and
So-
and that requires know-how, and it's application dependent, and it's not as
Yeah, yeah.
it's certainly not as clean as what you've presented.
Yeah.
It may be a lot easier and more palatable for an engineer to adopt, and that's
Yeah.
that's why I was asking.
Yeah, I agree with you. I mean, you can still come up with a threshold, but it might be conservative somehow because, okay, yeah, this is the problem is the threshold. If you're able to select it correctly, then you get
Yeah,
to this.
wondering with
Yeah,
threshold.
Yeah. Maybe I should have tried it for a certain threshold and see what can be get.
Let's thank Laurent.